Modern AI can write software, solve university-level mathematics, and even explain quantum physics. But what happens when we ask the same AI to learn a language it has barely seen before? The problem isn't just a lack of data. Before the model even starts learning, the structure of the language itself begins to fall apart. Instead of learning clear semantic patterns, the transformer is forced to learn from mathematical chaos. But what if mathematics could reveal the hidden structure inside a language? What if eigenvalues could tell us whether a transformer is learning meaningful patterns or simply memorizing noise? Imagine you're building the world's first large language model for an ancient language like Sanskrit. You've collected books, literature, poetry, philosophy, and centuries of knowledge. Everything is ready. Training begins. Every sentence is converted into numerical embeddings. Each word becomes a point inside a high-dimensional mathematical space. This is where the transformer begins learning the structure of a language. But not every embedding space is equally good. Some naturally organize similar concepts into meaningful directions. Others become noisy, scattered, and difficult for the model to learn from. When the geometry becomes disorganized, similar concepts may drift apart, while completely unrelated concepts become unexpectedly close together. The transformer now has to learn from a representation that contains far more noise than structure. So we add more data, millions of additional sentences, larger datasets, longer training, but a bigger dataset doesn't automatically create better mathematical structure. So, here's the real question. Before we improve a language model, how do we measure whether its embedding space is actually well organized? Surprisingly, the answer comes from one of the most beautiful ideas in linear algebra, eigenvalues. At this point, we know our language has become a cloud of mathematical points, but simply looking at the cloud doesn't tell us whether the transformer has learned meaningful structure or just random noise. Imagine rotating an invisible measuring stick around the embedding space. Every time we rotate it, we ask one simple question. Along this direction, how much information is actually present? Most directions contain only a little information, but eventually, one direction captures far more variation than every other direction. This isn't an accident. It is the most important direction hidden inside the language. This special direction is called an eigenvector. It represents the dominant semantic direction inside the embedding space. But finding the direction isn't enough. We also want to know how important that direction really is. The amount of information captured along that direction is measured by its eigenvalue. If one or two eigenvalues dominate, the language has learned strong semantic structure. But if the energy is spread almost equally across many directions, the embedding space is noisy and difficult for the transformer to organize. Mathematically, we build a covariance matrix from the embeddings. Eigenvalue decomposition then discovers the natural directions hidden inside that matrix and tells us exactly how much information each direction contains. Eigenvalues don't improve the language by themselves. They reveal its hidden geometry. Once we can measure that geometry, we can redesign tokenizers, embeddings, and training methods to produce cleaner and more meaningful semantic representations. Something remarkable has just happened. We discovered that only a handful of directions carry most of the information. So here's the next question. If 90% of the information lives in just a few directions, do we really need every dimension? Can we compress the language without losing its meaning? You may be wondering, didn't we already learn singular value decomposition? Why are we studying eigenvalues first? The answer is simple. Eigenvalues help us understand the geometry of the data. SVD helps us understand the geometry of the model. One analyzes the language itself. The other analyzes the neural network that learns that language. Eigenvalue decomposition works beautifully on square matrices like covariance matrices. But the weight matrices inside transformers are almost always rectangular. That's exactly where singular value decomposition becomes the more powerful tool. Eigenvalues tell us which directions are important, but they don't actually compress anything. So here's the next question. If only a handful of directions contain almost all the information, can we safely discard the rest? In the next episode, we'll see how principal component analysis uses eigenvalues to keep only the most informative directions, allowing us to compress high-dimensional language into a much smaller space while preserving almost everything that matters.